Thanks very much, Umberto, and pleasure to be here. I've occasionally been here in the past, but it has been a while. So it's fun to come down here and see all new facilities and new people and that sort of thing. I hope that the students are. We had this deal where the students weren't coming to be spectators at the basketball games, and so the university sent around an email and said, well, we'll offer you a free pizza if you come to the, and they all came. Okay, anyway, so I don't know. Hopefully the students are being rewarded. So I'm going to talk about silver and gold particles and things that you can do with them in terms of their optical properties. This has been a project that I've done. Let's see, I guess I do need to put this in here. This is a project that I've done with a number of absolutely terrific collaborators at Northwestern, and you'll see a lot of their results. But Terry Odom, Rick Viadyne, and Chad Merkin are the people who I'm going to sort of highlight today. If anything that appears on my slides that looks like an experiment, it was done by them, okay, or their group. In my group, I'm going to talk about electronic structure and also electrodynamics. The real star in the electrodynamics area was a guy named Marty Blaber, who has since moved on to real-world plasmonics applications in Seagate. Do you know that the next generation of disk drives are all going to have little gold nanorods that are in them that actually are crucial to the functioning of the disk drives? And then Nick Valley, you'll see a lot of his contributions in the electronic structure area. And we're going to talk about, first of all, just about, plasmon resonance properties of silver and gold particles is this sort of just bring us up to knowing what this is all about. And then we'll talk about SIRS and the surface-enhanced Raman scattering and how we can understand that. And there'll be both electromagnetic aspects to that and also chemical aspects to that. And then we'll talk about nanoparticle arrays and how that leads to some exciting opportunities as far as plasmon-exciton coupling, including the making of sub-wavelength lasers. This all begins with just this whole concept of the optical properties of silver and gold particles. Okay, I don't know if sometimes people can make these in labs, as undergraduates. Gold particles, gold colloid gold is a red-colored liquid. Okay, that consists of little, like 10 nanometer sized particles of gold that are suspended in water. Okay, this is the sort of thing that's been studied, for centuries. It's the same stuff as the red color of stained glass windows. This is an old topic in many respects. Colloidal silver is a yellow-colored liquid, same idea, but just a different material. In the case of gold, you see a big peak in the what's called the extinction spectrum. Extinction is absorption plus scattering, and occurs at 520 nanometers, so in the green region of the spectrum. Okay, so the red color actually is telling you about light that is not absorbed and not scattered, and that turns out to be in the red region of the spectrum at 600 nanometers. And so in the end, when you look at red, you're seeing the stuff that is not being absorbed and scattering. But the green color, 520 nanometers, is telling you about the oscillations of the conduction electrons in the particle. This is a standard picture that people draw where they're imagining that the conduction electrons are a cloud of electrons that oscillate relative to the nuclei, and there's some characteristic frequency of oscillation that depends on many things. Okay, it depends on the nature of the material. In other words, silver and gold are different, but it also depends on the shape of the particle, on the size of the particle, on what the surroundings of the particle is. If you have many particles, it depends on their arrangement relative to one another. And so in the end, this is a case where you can change the optical properties just by changing all these properties of the particles, which is different than, for example, you would have with organic dyes, where the organic dyes have a color that isn't changed, doesn't depend on exactly what the shape of the arrangement of the dyes is. Yeah, my former postdoc Marty Blaber made what he called the plasmonic periodic table. Okay, so in other words, what materials are actually useful for plasmonics? Okay, and in this table, he actually defined a couple of things. One has to do with just what's the frequency, in this case in electron volts, of the maximum in the absorption or extinction of the particles, and then the other one had to do with the some measure of the Q factor. Okay, so just in the sense of intensity. In this case, it's related to the ratio of just the frequency of the plasmon resonance divided by its width. So you can go through the periodic table and just calculate these numbers for anything. They have to be metallic. That's one issue. Well, there's a story about semiconductors, which is we won't get involved with. And then it turns out if you hunt through on this and ask what's the biggest Q factor, so Q factor is a big deal. And it turns out here it is, silver, 97 in this however he calculated these things, and it beats out everybody else on the periodic table. Okay, so that's why it is that everybody's focused on silver. And then if you ask the question, well, okay, so what's the next highest one? Okay, and it turns out actually it's potassium, but it turns out people don't like to do potassium experiments. Okay, I don't know, maybe Kathy can figure out how to do that stuff, but I don't know anybody that does potassium experiments. Anyways, so if you go and ask, well, what's the next one after that? Okay, well, sodium, but it turns out gold, okay, is right up there. Okay, so that's why everybody likes to do experiments on gold as well. Okay, and so that's what I'm going to talk about, silver and gold today. But there's other ones in the periodic table. Copper is not bad. We've done some work on copper. Aluminum is not bad. Especially aluminum is great for plasmonics in the UV. So so aluminum is a reasonable thing, but it has its issues, as you can imagine. We wrote some papers. Our paper last year that had to do with the plasmonic properties of what's called the poor metals. The poor metals are the ones that are kind of over here, okay? And, lead's possible. Just people don't seem terribly interested in lead, but it's possible. We did do some experiments with Odom on indium and gallium, which are okay. And then we've played around occasionally with other metals. We did one paper on palladium. Palladium has some interesting properties. It's not great, but it's okay. Anyway, so there's some other ones. There's sort of stories on everywhere in the periodic table, but somehow or another, when you look at this, you quickly focus on silver and gold. Okay, so that's what I'm going to talk about. So Gustav Mie was the guy who solved Maxwell's equations in all their glory back in 1908, and contained within his result is a way of understanding how plasmons work, in the sense that you can write a formula for the extinction cross-section, which depends on the real and imaginary part of the dielectric function of the metal. Okay, so the real part for a plasmonic material needs to be negative, and fortunately that's what metals are. Here's the real part for gold. All nice and negative, okay? And then you might notice that there's epsilon 1 plus 2, so whenever epsilon 1 is minus 2, okay, then you get something interesting happening. Well, it happens that in gold, that occurs at about 520 nanometers, and so if you just take these results, and the imaginary part needs to be small enough for interesting things to happen, then you get this peak, for example, in the gold case. And you can use classical electrodynamics to calculate the optical properties of metal particles. Here's a comparison of theory and experiment for spherical particles, and it works. Okay. Now it doesn't always work. Okay. Again, when you go to small enough particles, then there's deviations away from classical electrodynamics. But it works really quite well, and so that's really great, because that means that you can use classical electrodynamics to understand optical properties for lots of different things, and so that's what we do. Now, it turns out for spheres you can use Mie theory, but for anything else you have to use just numerical solutions of Maxwell's equations, and so we do that, and there's a whole bunch of different methods that have been developed, and it's all, in some respects, become a routine activity. But there are things where Maxwell's equations are not enough, and so we do go beyond conventional Maxwell's equations in some of the applications, and I'll mention a little bit about coupling quantum mechanics to electromagnetic theory later on. So I decided I'd talk about one project that has to do with some new stuff about the optical properties of isolated particles, okay, and this has to do with gold disks, okay, and this is a project that I just, well, I mean, again, it's Chad Merkin's group. There's a guy named Matt O'Brien who did absolutely terrific work in Chad's group, and what he did, so Chad's group had previously learned how to make triangular prisms of gold. These are single crystals, and they're really nice and perfect, except that the tips usually are truncated in some funny way, and so there's a lot of dispersion in the particle shapes, it turns out. But it turns out, what Matt discovered was that if you just take these guys and you add gold-3, some redox chemistry takes place. That this is the Kathy Murphy part of this talk. Okay, and you end up rounding off the tips. Okay, and in the end, you end up producing gold discs out of this, where the disc is basically the shape or the size of the disc is determined by basically inscribing circles inside of the triangle. It's actually quite remarkable that it works so well. And it turns out you can make gold discs that are very, very uniform as a result of applying this kind of chemistry. Okay, so then turns out if you measure the optical properties of these gold discs, so these are the extinction spectra that I was talking about before, and you can make gold discs of different sizes, so that leads to extinction at different wavelengths, and that's what you see right over here. This is the experimental data. You can just plug in and do a theoretical calculation of the extinction spectra, and theory and experiment match each other really well. And this is in spite of the fact that in the experiment there is some dispersity of particle structures, even as good as the disks are. So in the end, one of the things that we discovered about these gold disks is that they have, I think, what is the narrowest plasmon resonance for any gold particle. Okay, and of an electron volt. And it turns out there's reasons for this. Okay, things that we sort of, in a sense, knew but didn't realize how good the disks were for this property. Okay, so it turns out there's one of the issues that broadens plasmons is radiative damping. If you have particles with sharp points, okay, so triangles have sharp points. Rods have sharp points. Okay, they radiate really well, but it turns out that's a problem as far as getting narrow plasmon resonances. These circular disks have no sharp points, and so therefore they're much better than the other particles are. It turns out another thing that happens is that the conduction electrons in these metals, they have some intrinsic lifetime that would occur for a bulk metal. But what happens is that whenever the conduction electrons crash into the surfaces of the metal, which they can do, then that leads to a new type of source of dephasing of the conduction electrons. Okay, so there's the so-called surface scattering, which is the scattering of conduction electrons off of the surface of the particle that leads to a broadening of the plasmon resonances. Well, something that we discovered a couple of years ago in some work with Viadyne is that if you have these prismatic particles with flat surfaces, for whatever reason, the conduction electrons don't dephase when they scatter off of the flat surfaces. And so as a result, you'd think that the surface scattering should be really small when you get to particles that are only 7 nanometers in size, but instead there's no dephasing from surface scattering for prismatic single crystals. And so that's just what these are. They're prismatic single crystals. And so that's another issue. And then the third issue is that with any particle, you can have multiple plasmon resonances. So you don't just excite dipole oscillations of the electrons, you can excite quadrupole oscillations and other things. And it turns out that always broadens the plasmon because you have all these, not just one peak, but many peaks. But turns out with gold, all the out of plane plasmon modes in these gold disks are killed by inner band effects because they occur too blue in the spectrum. So gold is such that whenever you go to the blue of 500 nanometers, then you get into a regime where it's not very plasmonic. It's kind of you get the conduction electrons start interacting with d orbitals on the gold atoms, and so and that leads to additional sources of scattering that broadens the plasmon, and so in the end, these gold disks are such that the transverse modes are in the optical, or to the red of 500 nanometers, but the longitudinal ones are to the red of 500 nanometers, but the transverse ones that are bouncing up and down like this are to the blue, and so they get killed off. So there's this one measure of the quality of these materials is to look at the ratio of the transverse extinction to the longitudinal extinction. And here's the gold discs. They have much lower values than either do silver discs or gold rods. And so in the end, when you make gold discs that are on the order of 7 nanometers or so in thickness, then there's basically no transverse resonances at all. And so that means that these guys only have the longitudinal plasmons, and that's it. So it's a very, very simple result. Okay, so that's what you can do with individual gold disks. It turns out then it's like, oh, but recently we did some stuff with stacking gold disks. And if you come to my talk this afternoon, I'll finish the story. Okay, so somehow this part of it got divided between two talks, and so I apologize for that. But anyways, there are some neat things you can do when you stack the gold disks. All right, now we're going to talk about surface-enhanced Raman scattering. And this is an old paper from Chemical Engineers in 1983 in which they had an interview with this guy, Rick Viadyne. This is a 1983 picture. And in this, they were talking about the discovery of surface-enhanced Raman, which he was involved. His first paper was this paper in 1977. And this is just comparing the Raman spectrum of pyridine in solution, that's what this is, with pyridine adsorbed in a monolayer concentrations on silver, roughened silver particles. And it's a similar looking spectrum, but the key thing is that when you work out the intensity per molecule, there's some enhancement effect here that was 1,000,000 times larger than in this particular spectrum, just in terms of the number of molecules that are being irradiated, things like that. So that was a big mystery in 1983, okay, but already they were talking about the tremendous potential of this technology, okay, for various bioanalytical applications and all that kind of stuff. All right, so that was the story from long ago, but it did lead eventually to an understanding of the fact that there can be plasmon enhancement effects, the so-called electromagnetic mechanism of SIRS, that the molecules near the particle surfaces are experiencing these enhanced fields arising from plasmon excitation. And there's an enhancement factor estimate that is not too bad, in which you just say, oh, it's like E squared at the incident frequency times E squared at the Stokes shifted frequency, or roughly the 4th power of the field, and that's the plasmon enhancement factor. And back in 1983, the number was thought to be 10 to the 6th, but I'll show you later on that numbers even up to 10 to the 12th are possible. Okay, so that was that deal. Now, from subsequently, after, let's say 1983, all the particles were ugly. Okay, they were made with electrochemistry, things like that. Nowadays, of course, you can make particles, tailor-designed particles, and so then you can raise up this question about, well, okay, so what particles do you want to make? What are the best particles for SIRS applications? And so here I had somebody do some calculations where we chose particles. These are all silver particles that have plasmon maxima near 700 nanometers. Okay, and then it's like, then what is the value of this e to the 4th, say, averaged over the whole surface of the particle? So spheres, you just get a very small number in this case, but it turns out the best particles that we found were either rods or triangles. Okay, so that's why we focus in on rods and triangles. And you get numbers that are around 10 to the 6th in both cases. So that was the 1980s plasmon enhancement factor that you get from these particular applications. Okay, so that says that if you want to do isolated particles, then that's a reasonable thing to do. But in the same calculations, we also said, well, what happens if I take two rods and I stick them together end to end, okay, with a 2 nanometer gap? Okay, and it turns out that this average e to the 4th jumps from 10 to the 6th up to nearly 10 to the 8th. Okay, and so in the end, that's telling you, if I really want to do, large enhancement factors, then what I want to do is to make, in this case, rods with a small gap. In this case, the gap was 2 nanometers. But if you look at how this average e to the 4th varies with gap size, that's this plot right here, okay, then you discover, oh, it just gets bigger and bigger as you make the gap smaller and smaller. Okay, so that's really exciting. In fact, you can make a log-log plot of this, and that's this curve right here. It almost looks like it's linear in the small gap limit. Okay, so so e to the 4th would vary as 1 over the gap squared. So that really says, you need to make really small gaps. Okay, so that was the deal. Okay, in this case, we just stopped at 2 nanometers because we sort of didn't feel our calculations would be accurate for smaller gaps. But we have done smaller gaps, and it does keep going up. But it turns out that other things start happening when you get to gaps that are much smaller than a nanometer. Okay, and one of the issues is that you run into this case where electrons can start tunneling back and forth between the particles. Okay, and when that does, two things happen. One is that that shifts the plasmon resonances around in ways that are very hard to know what they're going to be, and the other one is that the enhancement factors get smaller. Okay, and so in the end, it turns out if you had your choice in this business, what you really want to do is to figure out how to make particles that have gaps that are 1 to 2 nanometers, okay, and controllably. Okay, so that's a challenge for the synthetic chemists. Okay, that's the unfortunate thing. It turns out in the Viadyne lab, they had particles that were just sitting around already that happened to be pretty good. So these are gold particles, dimers and trimers that are that actually were commercially. I don't know if they're still commercially available. At one time, there was a company that now is part of Cabot that was selling these things, and but basically they're gold particles. They have molecules coated on the surface of the particles, and then there's a silica shell that's put around it that is good for stabilization. And mostly they're monomers, but there's a small fraction of dimers and trimers and other aggregates. And these are the ones that are interesting because, well, you can't tell from this picture, but it turns out that very commonly there'll be gaps that are on the order of a nanometer between the particles. And sometimes they touch, and it turns out touching is okay too. Okay, so in the end, these have enhancement factors. These are Viadyne experiments, which are in the range of around 10 to the 8th. This is averaged over the entire particle surface. And so these are these pretty high enhancement factors that are now easily obtained as long as you, well, as I say, you know how to make particles that have the right gap size. Another thing the Viadyne groups noticed when they were doing these studies, so these are trimers, but dimers will do this too, is that when you look at the Rayleigh scattering spectra of these particles, so this is their measured Rayleigh scattering spectra, you get results where often there's more than one plasmon resonance. In this case, it sort of looks like there's two, but actually what it really is that there's two that are optically bright, and then there's additional ones that are optically dark. In particular, this minimum rate here, you can kind of dig into it, I'll show you in a second, and you'll see that there's actually still plasmon excitation occurring at these wavelengths. It's just that it doesn't couple with a far field. And so that was interesting because it was like, well, what happens in SIRS as far as this, when you have these multiple resonances are concerned? And so we did calculations of this. So this is the calculated Rayleigh spectrum that matches what the Viadyne group got. But what we also did was to calculate this e to the 4th enhancement factor. And what we found was that the e to the 4th enhancement factor didn't actually see all this structure in the extinction spectrum. That instead it was just very high uniformly over the wavelengths where the plasmons could be excited. Okay, so it was like, well, what was that all about? And also, at the time we did this particular study, there weren't any experiments. And so could one do experiments and show that you see this kind of behavior? So here's the theory part of it. So in this case, what I'm doing is we decided, well, let's look into this business about bright and dark resonances. And so in this case, what I'm showing you is this is what E squared looks like around the particles. This is a trimer that looks like this. And this one is a bright one, so that means then that you get big values of E squared, well away from where the particles are. And then this is one of these dark resonances, and what we see is that it's much darker, well away from where the particles are, but closer in, you still see plasmon excitation. It just doesn't couple to the light very well. And so in this case, if you take these particles and you ask what does E squared look like or E to the 4th look like closer in, this is the same trimer. And then if you take this little gap region right here and you blow that up, and then now we're looking at what E to the 4th looks like right in the crack between the particles, okay, and you get numbers that are 10 to the 12th for this bright resonance. So this is not the average E squared, E to the 4th value, it's now this peak value, okay, and over here in the dark resonance, you also get these contours that go up to 10 to the 12th. So it turns out that the dark resonances can still have very high values of this E to the 4th parameter. So that's explaining then why it is that this result was very flat in the region where the Rayleigh scattering spectra was showing lots of structure. Okay, and then they did do the experiment as well. So in this case, this is again this trimer, and here this is the scattering spectrum in red, and there's a resonance here, and there's one here, and there's actually one off to the right that they didn't see. Okay, here's the calculations of the same properties, and you can see it all looks very similar. And then this is the Raman excitation spectrum. So Raman intensity is a function of incident wavelength, and indeed they actually see the maximum in this intensity that occurs where the dark resonance is located. Similar, and that's again consistent with what the calculations were. So in the end, there's just all these tricks now that we just think of it as saying, oh, electromagnetics really does play a big role in all this Raman enhancement business, and you can play games with how to optimize Raman enhancements by dark resonances and tuning plasmon properties and things like that. And I think we know a lot about that now. All right, so now what I want to do is to talk about quantum mechanics for a little while, because there was always this question about in the SIRS business, there was always this thing about the so-called chemical enhancement factor in SIRS, and I want to kind of go in that direction with it. So there was always this thing about, well, can you describe plasmon resonances with quantum mechanics? Okay, and of course, can you describe optical properties with quantum mechanics? Yes. Okay, so it turns out there's a formula which says the extinction spectrum goes like the imaginary part of the frequency-dependent polarizability, and the Raman spectrum is the polarizability derivative squared. So that says then that we just need an electronic structure code that will calculate those properties, and then we can at least we can calculate optical properties with quantum mechanics. So that's actually available nowadays with time-dependent density functional theory. There's many codes out there. The one thing that we had to do was to calculate these on resonance for the electronic excitations of the whatever it is that we calculated, and so that's not so commonly available in electronic structure codes. But we modified a code called ADF that will do that. So then we could calculate the optical properties of, well, whatever we wanted, and we decided to study small silver clusters as a way of getting involved in this work. And this was all the work originally of a postdoc, Lasse Jensen, in collaboration with a guy named Jochen Aschbach, who's a quantum chemist. And so here's some results. Okay, so these are silver tetrahedra, in this case with 20 atoms in it. And what we got out of this was one very, very bright intraband excitation, and then a lot of interband excitations at higher energies. The intraband excitation, back in the days when we published this, we just said, well, this is sort of like a plasmon. There's been an evolution in thought on this, which says that no, this really is a plasmon. There's always this question about what is the minimum number of states that have to be simultaneously excited in order to think of it as a collective excitation. But you can dig into this and indeed find that collective behavior in this excitation, even though there's only one real optical transition that dominates the overall spectrum. Anyway, so that's what you get for silver 20. You go to 120 silver atoms, then you discover that you get more or less the same thing, but it's dramatically redshifted, which is telling you about these size-dependent effects. But then the other thing is that this intraband of transition now is really a cluster of many different excitations. Okay, and so that's what plasmons are all about, many different excitations. So I think this is actually more justifiably called a plasmon excitation. And it turns out you can then go on and do just standard electrodynamics calculations with experimentally determined dielectric functions, and you can calculate the spectrum for, again, another tetrahedrally shaped structure, in this case a much larger one, so that we don't have to worry about size-dependent effects. And you get a spectrum which is very similar, but again, further redshifted, which again is just telling you about size-dependent effects. Okay, so in the end, this is telling you, yes, quantum mechanics can give you results that are very similar to what you get with classical electrodynamics. Like catch with quantum mechanics is that you just can only go to so many atoms, and then you run out of gas with what you can do on a computer, and so you're stuck with, with on the order of 100 atoms or so with this sort of technology. Here, just showing you, this is silver 84, which is a similar kind of result where this is like a clump of all these individual transitions. And if you dig into this and you ask the question, well, what are the initial and final energy levels that are contained within this cluster? The answer is that it goes all the way from the Fermi energy below to h bar omega below the Fermi energy to h bar omega above the Fermi energy. So in other words, essentially every transition that's possible does contribute. And so that leads, if you ask the question, what does that lead to in terms of the distribution of excited energy levels at the end of the excitation? And the answer is that it leads to a very flat-looking distribution of these hot electrons. That's the terminology that people like to use in these excited clusters. And so, in principle, those electrons might be involved in some sort of chemical processes, although I'm not going to talk about that. And it contrasts with what you get if you look at an inner band transition going from the d orbitals up to the conduction band, where they're more localized near the Fermi level in these excitations. Okay, so we decided, well, let's try to do Raman. Let's calculate the Raman spectrum of, say, a 20-atom silver cluster with a pyridine molecule on it. Maybe this is like what CERS is all about. So we did that. This is the spectrum you get from polarized ability derivatives. This is the spectrum of just isolated pyridine with no silver particle. This is what you get with a silver particle. And, similar looking spectrum, but the intensities differ by 5 orders of magnitude. Okay, so that's the Raman effect. Here we would have both electromagnetic contributions and chemical contributions included in the calculations. And this Raman spectrum agrees reasonably well with what's actually seen in the experiments. So in that respect, this is a way of describing CERS that has all the right physics in it. What we discovered, unfortunately, is that it'd be nice if this were a robust method, but it's not. Okay, what we found is, time-dependent density functional theory in general has all these problems with self-interaction errors, and you end up getting these charge transfer states that are spurious. And it just happened with this particular system, the charge transfer states didn't get in the way, but in almost anything else we studied with this, the charge transfer states occurred at energies that excitation energies that were the ones we wanted to study. And so in the end, you couldn't really get reliable techniques or results with this method in general. So we evolved on to other methods. We had to figure out, well, okay, we need to have methods that include for electromagnetic effects, that include for chemical effects. How do we do that? And so one thing, you can do a calculation in which you just say, okay, I'm going to use classical electrodynamics to get the E field, and then use quantum mechanics on the molecule only, and get the Raman spectrum and just multiply the results together. And you can do that for pyridine, which is what the spectrum I'm showing you here. And it's sort of okay, but it doesn't give you the chemical effects. All right, so then how do we get the chemical effects? All right, so turns out Lasse Jensen, after he moved to Penn State, he got an idea that said that you can get the chemical effects by doing the time-dependent density function theory calculation on the combination of molecule plus metal cluster, but you just need to calculate the non-resonant part of it, the static Raman part of it. So that avoids these problems with these spurious charge transfer states, and that this would, however, still include at least the non-resonant component of the chemical enhancement factor. So he did some calculations where this is density functional theory, intensities for a whole bunch of different molecules, and then this is a 4-state model that he said, well, okay, the key thing is that it needs to somehow describe the effect of transitions going from the silver HOMO up to the LUMO of the molecule. And so he showed that there was a correlation of those things. What we decided to do with that idea was to actually do an experiment in which we studied a whole bunch of substituted benzene thiols and looked at their intensities and how do they vary, the intensity of a whole bunch of different molecules compare in the experimental data, okay, so this is experimental intensities as opposed to what we would calculate with the static limit DFT calculation. And, there is a reasonable correlation with these things. So in other words, think of this as so all the particles involved in these calculations were the same. So the electromagnetic calculation, part of the enhancement would be the same for all these different molecules. And the only thing you're changing is the chemical enhancement factor. And there's about a factor of 5 change in the chemical enhancement factor. And theory and experiment do correlate with one another. And this just mixes together results for silver and gold. And so it doesn't seem like the metal actually matters that much. All right, so that's a way of getting the chemical part of it. But now we want to combine those two things together. And what do you do with those? And so we did the obvious thing, which is say, okay, so now what we do is we get the fields out of electromagnetics, and we get the chemical enhancement out of this static limit DFT calculation, combine the two things together. Here I'm just showing you some results for Pyridine, which essentially just are the same kind of quality results that we got when we were just doing it with the purely quantum mechanical method that I said wasn't robust. So in the end, this is our best theory for this right now. It's not really elegant theory, but it does put all the right sort of factors into the calculation. All right, so I want to finish by talking about the arrays of silver and gold particles. Okay, so we were been interested in arrays of particles for a very long time. Somehow or another, we always thought that arrays would just be 1D or 2D arrays of spheres or maybe cylinders, something like that. But it turns out that the array business has gone wild lately. Okay, and in my talk this afternoon, I'll talk about all sorts of exotic arrays, okay, that are starting to appear, okay, and so there's many different things that are happening. But we're going to stay with the simple arrays, at least for this discussion. And so one thing that we did about, well, a little over 10 years ago, we said, okay, well, suppose I have an array of in this case, there's silver particles, and suppose that I ask the question, what are the properties of the plasmon resonance that you get when the particles are spaced by roughly the wavelength? Okay, so these spacings are huge. They're like 500 nanometer spacings. So normally, if I do molecular spectroscopy and I space molecules 500 nanometers apart from one another, they don't really interact with each other at all. Okay, at that distance. Okay, but it turns out but that's not true of nanoparticles. I can simply make the nanoparticles big enough so that they have very huge dipoles, and that those dipoles interact with one another. And so and this is what we found. Okay, so in this case, we found that if you had just a one-dimensional array, and the polarizations are as indicated right here, normally in silver particles there's a plasmon resonance about 400 nanometers, and there still is in these results. But what we found is that there was another peak in the spectrum that corresponded to the wavelength equal to the spacing. Okay, so in other words, the photonic resonance condition, the Bragg diffraction condition being satisfied. And so it turns out, so this is a case where even if they weren't silver particles, there would be a photonic resonance associated with this structure, just basically a diffraction effect. But in this case, you've got silver as well. So what happens is you mix together these two kinds of resonances with each other. So these are these hybrid resonances. Sometimes we call lattice plasmons is the term that's sometimes used for them. And they're really narrow. In this case, where I have 400 particles in a line, they have a width of about 4 millivolts, which is very narrow. And it turns out if you go to an infinite array, they even get narrower. And so that was kind of interesting, because there's many different technologies of sensing and so on where the width of the line ends up determining your ability to resolve some detection technology. And so in the end, hey, we should try to do this. There weren't any experiments at the time that we did these calculations that talked about this. There were some earlier theories. Sometimes people debate who did this first. Okay, there were some earlier papers that touched on pieces of the story. So in the end, so there weren't any experiments, but quickly, Viadyne jumped in and tried to do an experiment. It didn't work very well. And other people tried it and didn't work very well. And so it was like, oh dear, this is not looking like it's going in the right direction. Okay, but it was a matter of just the technology of making arrays of particles wasn't really what it needed to be. This is the Viadyne experiment. They were trying to use E-beam methods to make particles. And what they saw was something where as you increase the spacing of the particles, this peak in the plasmon did move to the red, which was the same kind of result. This is the calculations for the same thing, and that was what was shown. But we never saw the narrow lines. Okay, so anyways, fortunately, the experiments got better. Okay, and a whole bunch of different groups, starting about 5 years ago, started getting results that showed really sharp line shapes. It was just really making the arrays, was with great perfection, and there's some issues about index matching and optics configurations and things like that. One of the people that kind of went in this direction was my colleague Terry Odom. And so here's some results that she generated, in this case using arrays of gold cylinders. And here's calculations that you can do for the same thing in a theory and experiment right on top of each other. I mean, it really does work. And so you can make these lattice plasmon modes, and you could study dispersion behavior and many different other kinds of just purely optical properties. But then it was like, okay, what can we do with this that's actually useful in some sense? So there were some predictions in the literature about making plasmon lasers that were interesting. So this is actually some work that, well, various groups. There was a group that involved Nogara, Shaleo, Stockman, many people that was published, in which they put, in this case, gold particles with a spherical shell that has laser dye molecules embedded in it, and they saw narrowed lines. But it turns out ever since this paper got published, people have been debating about it, because there's another thing that can give you narrowed lines. It's called amplified spontaneous emission. And it turns out that there's this, is it lasing, is it amplified spontaneous emission? And anyway, so this is where the people debate about this paper. Anyways, there's another one. There's the Zhang group at Berkeley. They did cadmium selenide nanowires that were next to a flat silver surface. So you get plasmon resonances at the sort of the gap between the two, and that can lead to enhanced lasing properties. And they saw these also narrowed lines and so forth. And I don't think people, I think people really believe in this experiment. So maybe this was the first of these lasing experiments. But anyway, so it occurred to Terry Odom that maybe what you could do is use these lattice plasmons as a way of enhancing the lasing by laser dyes. So they developed an experiment in which you have this array of gold particles, and then you put laser dye, basically just spread it on, pour it on, and then it's a optically pumped laser system. So there's a couple of experimental results here. This is just the extinction spectra of the array. But they did it with silver, gold, titanium, and TiO2, so the latter two things are not plasmonic. And so in this case, then you don't have lattice plasmons. But for silver and gold, you do. And here's the lattice plasmon right here. And then this other peak is just, there's laser dye in these experiments, and so the laser dyes are just, they're emitting what frequency they emit at. And then over here, they're actually looking at the emission of the system. And so the silver and gold show nice sharp emission spectra at the lattice plasmon wavelengths, and then the titanium and TiO2 don't do that. They just show non-laser emission from the dye. And then they have looked at pump energy dependence, so lasers are ones where there's some minimum pump power that you need to have in order for this to work, and that's what they see in this result. And they also, the other thing is that, of course, lasers are supposed to be like a beam of light. Okay, and so in this case, they looked at the width of the beam of light 15 centimeters above the surface, and indeed it was only about a degree or so. So things are consistent with this being a laser. And so we got interested in this problem, and so if you want to describe a laser with a theoretical model, then you need to have some sort of four-level system. So we replaced the laser dye photophysics with a four-level model that has both stimulated and spontaneous emission terms are included in it. And then, actually, let me jump here. You then take that, this is the four-level rate equation description of the system. So obviously, there's issues about is the rate equation model correct? But this is what we used. And then this is the Maxwell's equations. And so you couple all these things together along with a sort of equation of motion that describes the evolution of the polarization in response to the applied field. So you could solve all these equations and then simultaneously, and then you can make predictions about the properties of these things. So we did first of all, you have to make sure the extinction spectrum comes out right. So that's what I'm showing you here. Okay, it's just the comparison of extinction spectra. But then the other thing is the lasing properties. Okay, so in this case, I'm looking at emission as a function of input power, and theory and experiment are showing, yes, indeed, for silver and gold, we get results that are similar to the experiments. And then for the titanium and TiO2, we don't see anything. And this is just showing you where the population inversion is large, and this is the cylinder particles, and it's only large close to the particles. And then this is just showing you that the population inversion gets pinned above the lasing threshold, which is another thing that lasers do. And so it's all consistent with the idea that it's a laser. All right, so that's where we are in this direction, and I hope that I've convinced you. Well, there's all sorts of interesting phenomena associated with silver and gold particles, and we've kind of pushed in the direction of understanding SIRS. We've pushed in trying to understand both the chemical and the electromagnetic contributions, and then very recently we got involved in the laser issue using these plasmon lattice modes, and that, theory seems to be very useful in making predictions about all these different properties. All right, thanks very much.
Does anyone have questions?
Hey, nice. In the 4-level system that you're talking about, there are all 4 of the levels related to the dyes, or is there somehow?
They're the dyes. That's right.
Okay, so I'm trying to understand how what is the role of the plasmon enhancing? Is it just providing higher fields to excite the dyes mainly?
Yes. So that's right. So this is obviously this is a mixed theory where you're doing quantum mechanics for the dye, sort of, and then you're doing the classical electrodynamics for the particles. Okay, and so that's it. Of course, in the end, the dye molecules are they're spread out relative to the particles. There probably is some problems. The dye molecules that are within a few nanometers of the particle are probably strongly quenched by the particles. We're actually leaving that part out because there isn't too many of them. They don't really contribute very much. The dye molecules that are most significant to lasing are between, say, 10 nanometers and about 50 nanometers from the particles. And so there's been a lot of studies of plasmon-enhanced fluorescence, which basically says, yes, it's mostly just the laser field, or sorry, the field of the arising from plasmon excitation in the particle that enhances the emission associated with the dye molecules. And so that's and we do include, there's actually I forgot to mention that, so you get enhanced stimulated emission, that's the lasing part of it. But the other aspect is that there's a local density of optical states that is what feeds into the amplified spontaneous emission. Okay, so that's this whole argument about when is amplified spontaneous emission is included. And so we do include that factor, okay, so in these calculations, so that so if amplified spontaneous emission was important, then it would be contained in there, but we've kind of dug into the details and we find that it's actually the stimulated emission which is dominating well, above the laser threshold, the observed emission characteristics. Right.